So hi everyone, this is lecture 4 of the Google Developer Student Club. I'm David, and today we're going to be going over neural networks. What's a neuron? What's a layer? What's a network? How do they work? And what is backpropagation? So let's start. Let me just get my notes. Okay, so we're gonna go over what we covered last week very briefly, which is what is a neuron. So a neuron should write way bigger than that. A neuron is going to take in an input, if you remember, x1 to xm, it's a vector, and it's going to enter your node, which has associated weights, a weight vector to it. To enter the neuron, or node neuron is really the same thing, however you want to call it. The output of the neuron is the pre-activation, Z. Pre-activation. And then with the pre-activation, it will enter f of z, which is our activation function. F is really the activation function. F of z is z's the input. And then output of the neuron is simply the activation A. So that's basically what a neuron is. We're giving a input vector into the neuron, which has associated weight matrix, and then we're outputting an activation. That input or that output is being inputted into the activation function, and then we get an output for the neuron. So quickly, let me just go over what our activation looks like. So our activation A is equal to f of z. That's obvious from the diagram, which is, what is z? Z here, z is the sum from k equals 1 to m. K is just the dummy variable of xj w or xk wk plus your offset, which is just a bias. So these are your weight, you have your input. It's the dot product between your input and your weight vector. So we have a xm input, x is a m by 1 vector, and w is n by 1. Yeah. And you're going to do the dot product between those. And then your output is going to be n by 1. So f here, your activation function. Yeah. Yeah, I believe I matched the. Yeah, sorry. That's good. So f is going to be n by 1. So yeah, w. 1 second. Just give me 1 second. I want to make sure I have the dimensions right. Okay. Forget the dimensions for now. I'll cover them again later because the notation is going to change. So f here, your activation function, is being applied element-wise. Okay? So every input of the output's going to be n by 1 for your activation, but every element of that n by 1 vector is the function is going to be applied to. So let me write down, basically, we'll get there when we get to writing out as a layer. So that's for simplicity, that's a neuron. Okay. What is now a layer? A layer is simply neurons stacked on top of each other. There are many types of layers in neural networks. Right now, we're going to talk about, just for today, we're going to talk about fully connected layers. So what does it mean for a layer to be fully connected? It's that your input vector, x1 to xm, each input, these will represent neurons. These are the pre-activations. And then we have our F's, our activation function, and then our output. Okay, so each neuron is really ran in parallel, stacked on top of one another, and fully connected means for every input, it goes to every neuron. Okay. So every input maps to every neuron, enters the neuron, is multiplied by the weight matrix. Out goes the pre-activation into the activation function. So in a fully connected layer, we're gonna have W, which is gonna represent your weight matrix. So you're gonna have M by N, an M by N weight matrix. Okay. So M by N, your bias, W naught, is going to be N by 1 because our output is N by 1. And okay, and how do we write our activation? Yeah, and our X is going to be M by 1. I believe I said it correctly earlier, but just these are the right dimensions. Okay, so F of Z is going to be it is going to be pretty much what we wrote before. It's what is Z? It's going to be W, your weight matrix transposed, times X plus W naught. That's why, since this is M by N, when we transpose it, our W is M by N, but W transposed is N by M. And then we're multiplying it by M by 1, doing the dot product. And then we're gonna, this results, if you remember from linear algebra, to an N by 1. So this is N by 1. This is also N by 1. And then the output is therefore, this whole thing is N by 1. So we're gonna have F here, F of Z, where Z is an N by 1 vector. Okay, and so we have a column vector that's N by 1 here with a bunch of Z0, Z1, dot, 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 Zn minus 1. Okay, so what F of Z would be is I'm going to apply F element-wise. This is important. Well, it'll be important when we talk about the backpropagation later. But we're applying our activation function to every element in the in Z. Okay, makes sense. Hope that's clear. If you have any questions, could write in the chat. Okay, so that is what a layer is. So to recap, fully connected layer, every one of the inputs maps to every neuron, okay, in the layer. And then Z, our pre-activation, so the output of that neuron is going to be your weight matrix, which represents all the neurons, times your input, plus your bias, your offset. Okay, and that Z is N by 1, and then you're going to apply F, your activation function, element-wise. All right, so yeah, that's pretty much it. Okay, so now before we talk about different types of activation functions, we're going to talk about what is a network. Well, it's pretty self-explanatory. A network is just running or connecting many layers in series. All right, so we're going to have same as before, really. Pretend these are fully connected, and also this is a feed-forward network. So what does that mean? That's what we're gonna talk about is networks that are acyclic. So all the network that we're gonna be talking about today just goes in one direction. It's like a tree. It has no cycles, so you can't go back. All right. So once an input passes through a layer, it can't go to the back. It has to go to the next layer. Okay. So all right. So we're gonna have our input X, which we could really think about as our zeroth activation. Okay. It'll make sense maybe later, but we're gonna pretend this is our layer. So we're gonna have our weight matrix, W1. Yeah. Yeah, W1, W0, 1. So our weight and our bias, okay? And then the output is going to be Z1. This is going to be inputted into F1, which is our activation function, or pretend they're all the same, but you could have different activation functions, different types of layers. So your first layer is your input layer. In between is your hidden layers. Your last layer is your output layer. That's just convention. So we're gonna continue the diagram. The output of our first activation function is A1, which is going to be then inputted into our next layer, W2, W02. Okay, so our second layer with weights W2 and bias W02. So you see now how this is really A0 because it's the same thing. You input an activation, you input the input is really the same as the activation, okay? And that layer takes in an activation or an input, okay? So output of this is Z2, which is fed into your second activation function. And then we're gonna go dot, dot, dot. This room. We're gonna go dot, 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 and then we're gonna get to your last layer. AL is being inputted into WL. Yeah, WL, W not L, which is then ZL. And then we have FL. Oh, sorry, this is AL minus 1. This should all be, yeah, this is AL minus 1. This is the last layer. F of L, and then output is AL, your last activation, which gets inputted into our loss. I hope you guys could see. Yeah, okay. So we have our input X into our first layer of neurons, our fully connected layer with weight matrix W1, W0. Then we have our pre-activation. Then we have it goes into our activation function. Then we're going to have our activation, which goes into our next layer. Keep going, keep going, keep going. So we get to the last layer where we have our last weight matrix, and it gets input into our loss function. All right, so that's a feed-forward network. It's really just putting these all in series and running them. So any questions? That's pretty much what a neural network is. You have your input layer. These are all your hidden layers. And then you have your output layer. Okay, and it goes into the loss function. So now, so the output is X. Wait, so the output is of A1 is the input of A2. The output of A.
Like
Yeah.
the question is mainly like I'm trying to understand. You only have one input, but you're going through the layers. What's like, because I'm just trying to figure out like
Yeah,
for W1 you put in X. You put in the input X.
Yeah, so remember what Z is? It's W.
The pre-activation.
Yeah, it's the pre-activation. It's W, the weight matrix transpose plus
the bias, yeah.
the sum. Okay. Okay. So that's this part here. So
Yeah.
we're inputting X to get Z. Okay. And then with Z, we're inputting it into our activation function. We haven't gone over that yet, but it's gonna somehow transform Z. Okay.
And then it's gonna fit into the next layer.
We're gonna talk like for now, we're gonna see what happens when F is the identity function. So F is just F of Z is equal to Z. So you don't do anything.
Okay.
So just pretend it's like that for now. So F of Z, Z. So it doesn't really, it does something like you could, it's not interesting in this case. It does something, but it's just linear. So it's just gonna output Z.
Okay. So
and then that's gonna go into the second layer.
okay, so it's usable. That's why. Okay.
Does that make sense?
Yep. Okay. Thank you.
Okay. So what happens? Yeah. What happens when you're what happens when f of z is Z? Okay. So let me I wish I had more, you could see the entire board, but we'll have to erase this. Try to keep a mental image. All right. Okay. So we know what Z is. Z is equal to your weight matrix transpose times X plus omega naught. Okay. So now this is also, let's assume f of Z is Z. So that would also mean your activation is Z. Okay, so the output of your layer or after your activation function is just simply the pre-activation. All right, so what does that mean? Let's ignore the let's ignore the bias for now, just so it's easier to understand. Basically, how do we write this? So we could say for our last activation, AL. Okay, if you remember, the last output of our network was AL. We could say that AL is WL transpose times the input. And what was the input to that layer? It was X. But remember what I said X was? X is technically like A0. So if I have WL, the input is AL minus 1. So if I had the first layer, the input's A0. Okay? So A1 would be WL transpose or W1 transposed times A0. So that's why X is pretty much the same thing as A0. Okay? So what is now AL minus 1? AL minus 1 is WL minus 1 transposed times AL minus 2. Okay? And we could keep doing this and keep doing this. And basically, we can keep going down and down. And then we're going to get to the end. We're going to get to basically AL or A1, okay, times or A0 times W1. Okay, so W1 transpose. So what did we do here? We simply did, if our activation function is linear, if it's f of z is z, what we're doing is just multiplying all the weights. Okay, so that's what we get. We get multiply all the weights times x or A0. Okay, so what does that really mean? We're multiplying m by n matrices, or n, it would be n by m because it's transposed. We're gonna get n by 1 output, sure, but we're just gonna get the same. We're gonna get an m by n times an m by n, or if we multiply all these matrices, we're just gonna get the same, a same m by n matrix. Okay, so we're gonna get W total transposed times x, which is, we didn't even need a neural network. This was just, we didn't do anything to x. We didn't do anything interesting. We just scaled it by some weight matrix. Okay, so we didn't accomplish anything by having a linear activation function. We need to run an x through an entire network. It's just a linear transformation. So if we have a linear function, we're going to get a linear output on our activation. So that's why it's not that interesting if we use a linear function. We want something nonlinear. Okay, so any questions before we move on? There's basically, there's no point of having linear functions for activation functions. They should be nonlinear for them to be interesting. All right, so let's talk about a few types of activation functions, and there are many types, but a key factor is that they're differentiable, and that's important because we'll have to take the gradient for gradient descent, which we'll talk about when we do backpropagation. So we're going to talk about the sigmoid activation. Okay. So we have sigma of z is just 1 over 1 plus e to the negative z. So this is going to ensure us that the output of this function will be bounded between 0 and 1, because the graph of this function looks something like this. That's a bad drawing. It's way more curved. That's better. Okay. So this is 0. This is your vertical asymptote. And this is not drawn to scale, but it'll hit here at 0.5. Okay. So this is, by the way, this is A. Okay. So this is one. Okay, I don't know if the zoom. It says I have like 10 more minutes, but maybe we'll restart the recording and just go from there. Okay, so basically we'll have our sigmoid activation is simply this function, and it'll map our inputs between 0 and 1. So this is very good for a binary classification problem. Let's say we want to give our input vector of something, and we want to map it to an input between 0 and 1, this is a function that you could use for your activation function in your layer. Okay, so that's just one example. Another example is rectified linear unit, which is ReLU for short. And it's simply the max between 0 and Z. So what does that look like? It's 0 here, that's negative, and it's linear after. Okay, so this is another example of another activation function. Depends on the type of problem you're tackling. You want to design your network to have a certain activation function if you're coding your own network from scratch. So that's another example. There's also there's also hyperbolic tan. This should hit 0. Okay. This goes to 1, to -1. There's vertical asymptotes here. Okay. So this is another example of if you want your output of your network to be between 1 and -1. Again, many different types of problems would deserve that type of output. So again, you're choosing your loss function, you're choosing your activation function, as I mentioned before, based on the problem that you're doing, the type of data you're dealing with, or not really the data, but the type of problem you're dealing with, it will depend on your activation, okay, and your loss. So all right, now let's talk about, we're pretty much getting into backpropagation. All right. So okay. So assume we have some loss function. What do we want to do? Generally, we want to minimize it. Okay, so how are we doing that? Well, we're going to want to minimize the sum of all of our losses that we have n signifies neural net. Okay, so all the losses from our network, and the inputs are wix. Sorry, xi x. Okay. So yeah, we're inputting our network into a network. This is Z, okay, and then we're computing the loss on that. So how do we minimize that? If you remember from last week, we're using gradient descent. So we want to pick the weights to minimize the loss. Okay, so remember we're talking about optimization algorithms. We have this multi-dimensional function. We want to find local or global minimum. How do we do that? We're going to go and travel in the direction that's opposite to the gradient. Assuming by convention you mean gradient is in the direction of greatest increase, you're traveling opposite to it because it's greatest decrease. Okay, so this is assuming your function is concave. All right, so we want to again pick the weights to minimize loss. How do we do that? Gradient descent. what we need to do that, we need to calculate the gradient in terms of the weights of your loss function. All right, so how do we do that? All right, so we're gonna go over backpropagation just to recap. We have our activation, our zeroth activation goes through our first layer, which is our first layer of weights. Then we get our pre-activation, our activation function. Keep going along to our last layer. It's input into the loss function. We calculate the loss. Now we have a prediction, we have a guess, and we have an actual to compare with. We'll get a value for our loss, but how do we update our weights? The way we do this is with backpropagation. So I want to know who caused the problem along the way. What weight layer do I have to change, or who do I have to blame that caused the problem? So we're going to tackle this with the chain rule. So I want to know the change in loss with respect to my weight layer. And we're going to just talk about the last layer for now, okay? Then we're going to connect it back to the first layer. So at the last layer, what's going on? I want to figure out how did my loss change with respect to my weight matrix. Okay, so to calculate this, I can break this down using the chain rule. So I could write the change in my loss with respect to my last activation layer, okay, times the change. One second. Let me just make sure. Yeah. Okay, the change in my loss, or the change in my last activation layer with respect to my last weight matrix. Okay, so to find this, how did our loss change with respect to our last layer? We have to be able to calculate or have a way to represent how our loss changed with respect to our last activation layer, and how our last activation layer changed with respect to our weight matrix from our node. Okay, so how do we break this down? Okay, so the change in loss with respect to our activation layer, what does that look like? So if you remember, okay, our activation layer, our last activation is F fed in given our pre-activation. So how our loss is changing with respect to our last activation is really just F. So what would the derivative or partial derivative be? All this is here is F prime. Okay, it's how our loss is changing with respect to our last activation is basically the change in our activation function. All right, so that's easy to calculate. Now, getting to this portion, it's a little more complicated. This is pretty straightforward. So the change in our last activation with respect to our weight layer could be broken down further with the chain rule. All right, so we have the change in our last layer with respect to our weight times okay, that is this is equal with respect to our pre-activation, and then we use chain rule to just break it down. Yeah, what's up?
Those supposed to be A's?
Yeah, these are A's.
They look like T's.
No, there is. Okay, so that's our activation. Okay, the change in our activation layer with respect to our weight layer could be broken down using chain rule and written as the change in our last layer with respect to our pre-activation times the change of our pre-activation with respect to the weight of our last layer. It's just chain rule to break it down. Okay, now we have to figure out what these two terms mean. Okay, let's start with this end. Okay, so let's start with this portion. Okay. I could write it. Okay, so the change in Z, or pre-activation, with respect to our weight, the last weight layer. So what is Z? Z, if you remember, A is equal to our activation function inputted with our pre-activation, which is just F of X W transpose plus our bias. Okay, so this is Z. Okay, so Z of our last layer is simply the partial derivative of our last layer transposed times X, or times pretty much what is X? Forget the bias for now, doesn't really matter. Okay, what is X? X is remember, X is our activation from the previous layer. Okay, so we're looking at the last layer and we want to know what our pre-activation is. Our pre-activation is going to be the activation or our input of that layer, which is the activation of the previous layer into or it's the output of our neuron. Okay, so it's WL transposed times AL minus 1. Okay. Now, basically, if we want to know how our weight or how our pre-activation is changing with respect to our weight matrix, we could write Z as such. Okay, it's the same thing. Now, if I'm asking you, how does W times AL minus 1 change with respect to W? It's really just AL minus 1, roughly. Okay, I mean, that's clear to see. Okay, so now getting back to this term here, how is AL changing with respect to our pre-activation? So to recap, this is F prime, okay, of Z, L. This is AL minus 1. Now what is this? This is our last thing we have to get to. Okay, so if you remember, we're applying F element-wise. So here, AL is going to be a vector, and ZL is going to be a vector. Now, the derivative of a vector with respect to a vector is generally going to be a matrix. All right? So if AL is NL by 1 and ZL is NL by 1, the partial derivatives is going to be a NL by NL matrix. Okay? So what does this mean? If you remember, how are we applying F? How are we applying F to get our activation? Okay, we're applying F element-wise. So what does that mean? It means that AL and ZL are only going to be changing with respect to their own values. So the first ZL1, I guess, is going to only depend on AL1 because it's applied element-wise. And AL2 is only going to depend on ZL2. Now, what does that look like in terms of a matrix? Well, we're going to have the partial derivatives of AI by ZJ. Okay. Now, this is what this looks like. It's a matrix of these partial derivatives. Okay, because we have two vectors, we're taking their partial derivatives, we're gonna get a matrix. Okay, because we have to do it for each value. Okay, we're gonna get an NL by NL matrix. Okay, does that make? I hope that makes sense. Okay, so since f is being applied element wise, the only values that are gonna get filled up are the main diagonal, okay, of this matrix. The rest is gonna be 0. So it's just gonna be a diagonal matrix. Okay. Now, since f is applied element wise, this is what this matrix is gonna look like, which is really again just f prime of z. Okay, it's these partial derivatives. Since it's applied element wise. All right. So to recap, what is this gonna look like? I'm gonna have to erase some of this, but to recap, we want to find basically what caused the most amount of trouble. Okay, so we have all these terms, and now we're going to travel back. We have basically a representation of how we broke down our loss function, what we want basically of this network. We broke it down in terms of chain rule, and then we figured out what every one of these represented. Okay, this was simply f prime, okay, of ZL. Then this portion was AL minus 1, and then this was also pretty much f prime. Okay, so we could use that to now we're going to travel back to the network and through the network and figure out who to blame. We want to figure out how our loss is changing in our first layer because we only did the last layer. That's again simply just a chain rule. So we now know what every term means. Okay, so we now know every term means, so we could simply travel from the end of the network back to the front, have all these partial derivatives that we compute along the way, or we have really already have a representation for each of them. So that's how we adjust this, our weights. Okay, we're traveling backwards through the network, and then we're figuring out who caused the most amount of trouble, or who caused the most amount of loss at each step. Okay, so again, from here, we're running back through the network and saying here, oh, how did my loss change with respect to my last activation? Okay, and then this is passed through, how did my loss change with respect to our pre-activation? And then how did my loss change with respect to my last layer? Okay, so the reason why we could do it by traveling forward, the reason why we have a forward pass and a backward pass, we could simply compute the gradients along the way. We want to figure out the gradient. We want to do gradient descent at the end of the day. Okay, we want to find the we want to travel opposite to the gradient, find our local optimum. Okay, so we're trying to figure out who to blame for that loss. Okay, how mad we were is caused by one of these terms. Okay, so we're gonna figure out who caused the biggest change in the gradient. Okay, or who caused the biggest change in that loss. Okay, so that's why we travel backwards through the network. It's because we already have a definition for all these terms we computed along the way. We're just going back and doing the same thing. We could go forward, but as you may know, when you're taking derivatives and you're not doing chain rule, you're just taking derivatives, you're computing a lot of redundant terms. Things repeat. a lot. This way, we already computed things along the way, and we're just going backwards, okay, using the chain rule, okay? We have all these terms, we know what they are. So that is why backpropagation works. It could train a network 1,000,000 times faster than traveling just forward through the network, computing the gradient at each step, then adjusting the matrix, then keep going and keep going. We run it through our input through the entire way, compute our loss, and then adjust as we go back. All right. So that's backpropagation. That's why it's important. And I hope you understand. Leave me any questions or anything in the comments. And that's it. Thank you so much. Bye-bye.